So to understand thin film interference, we have to start with the idea of reflection of waves. Remember, we showed an animation of how waves reflect off of different types of mediums. If you've got a wave, we had the animation where we had a wave which travels to a fixed end. And when the wave strikes that flip end and is reflected, what does it look like? It's inverted when it comes back. So when the wave comes back, it comes back inverted from the wall. Now, all this behavior is true for all waves. So sound waves do this, or not sound waves because sound waves are longitudinal, but any transverse wave. So string waves would do this, but light is a transverse wave, so light actually obeys this behavior as well. When it strikes a medium where the index is greater than the medium that it starts with, it reflects the wave back with what we call 180 degrees phase shift. Phase shift. Basically, that means it reflects back the wave inverted from when it came. Now, that's only when the medium that it's entering into is higher. If the medium is lower than it's entering into, it reflects back the wave, but it reflects it back as an open end or a free end reflection. And that was the reflection that we talked about with the free end, free to move up and down. When the wave is reflected off of this, it gets reflected back in the same orientation which it came in. So there's no phase change, there's no inversion. Taking that idea, when a wave comes into a medium, and this medium is, say, oil on top of water, and it's coming from air, oil will have an index of refraction of, say, 1.5. Water would have an index of refraction of 1.3, and air has an index of 1.0. So oil film on top of water. If you've ever seen oil film on top of water, you know what I'm talking about. It's got little kind of glossy, different colors. Maybe you see green, maybe reds or blues in there as well. So when light waves come and they strike a surface, they go through that surface if the surface is transparent or translucent. But in all surfaces, they also reflect off of as well. Even glass surfaces, if you take a laser beam and shoot it off a glass, it goes through that glass, but it also partially gets reflected. So that's true off all surfaces. So this wave comes in, and it's partially reflected. It goes into the substance and refracts, so it bends. And then when it hits the new surface, it refracts again. In this case, it would bend back away from the normal lines. It's going into a smaller index. And it's reflected and refracted again as it leaves. Well, these two waves up here, this one and this one, are the ones that we're concerned about, because those are the ones that we're going to see from the outside. So when we look at this light, here's our eye, looking at these light waves, those light waves will interfere with each other and cause a new, basically an interference pattern. Now that pattern will result in sometimes darkness, complete darkness, sometimes amplified light, and sometimes in between it'll cause colors to appear. Now why would these two waves interfere with each other? Well, if one wave is coming up looking like that, remember light is a transverse wave, and the other wave is coming looking like this, those two waves would interfere destructively and cancel each other out. So you would see black lines in that situation. So we concern ourselves with at what point or at what thickness of the oil, thickness, I don't know what you want to call it, T for thickness, D maybe? Maybe D is better since we're talking about distances. At what thickness of oil do we see different colors, or what thickness of oil do we see black, or what thickness of oil do we see constructive interference? Well, it all has to do with how far that wave travels through there. So let's take a kind of a wave approach to this. Let's say the light wave is coming in looking like this. So can I wonder if I could do this. Yeah, I want this. So identical light waves. Oops. So the light wave comes into the medium in this direction, and it's coming into the medium and reflecting. Now, if this is oil and water like it was before, and air, then when the light wave strikes the air and is reflected, does it undergo a phase change at the first medium? Yes, because the index of the medium is higher than the index it's coming from. So it phase changes. So this wave actually basically flips upside down as it's leaving. So it's changed its phase. The wave partially goes through the new medium too, so it comes through here and it travels and it strikes a new surface. Now it doesn't undergo a phase change here because we have a high index, 1.5 going to 1.3. So it just reflects normally. It reflects in the same orientation that it came in at. So it's coming out. And then when it goes from oil into air, we're not talking about a reflection, we're just talking about transmission, so no phase change there. And then it comes out. So the question is, how is the crest of this one line up with the crest of that one? Well, if the crest lines up with a crest, if they're in phase with each other, you have magnification, or amplification rather. If a crest lines up with a trough, then you have destructive interference. Try to bear with me with this. This is a little bit complicated of an example of how we go about solving this. This one is upside down compared to the one that's coming out on the other side. So if the light wave here travels one full wavelength, then they'll destructively interfere with each other. So if this distance that it travels, the path here, if that path, I don't know what we'll call it, x1 and x2, is equal to a full wavelength, when this one comes out, it will be completely opposite. So you'll end up with destructive interference. If that path length, x1 and x2, the path that this thing travels, is equal to a half of a wavelength, then you end up with constructive interference. So what is that path length that that thing is actually traveling? Let's come back to that idea. Let's look at it if it were just traveling straight in. It reflects, and it reflects, use green for the reflected way. It reflects opposite. So that's what it looks like when it comes off. The wave then keeps traveling through and reflects, and this time it reflects back with the same orientation. And there's the distance d. Now, if d, in this case, is a full wavelength, we have destructive interference. Destructive. How thick does d need to be in terms of lambda? One half a lambda. So it's half of a wavelength, because it's traveling there and back, then you get destructive interference. If d is a full wavelength, or any multiple of a full wavelength, then you'll get constructive interference. Now let's take a look back at this idea. We kind of already said it, but we can't just say x and x1 and x2. We have to put it in terms of d. Well, this is where it gets a little bit hairy because you have to combine it with Snell's law. When this thing is projected through here, you will know the angle at which it's projected through if you know the angle at which it comes at. Right? Snell's law will allow you to solve for that angle. Well, now what is the distance x1 here? It's sine of theta equals, oh no, cosine theta, huh? Cosine theta equals d over x1. So x1 equals d over cosine theta. Now, that's just for this example. x2 will be the same, so 2d cosine theta. If that equals a wavelength or any multiple of a wavelength, then you get destructive interference. You have to take your time and look at the problem. The important thing to know is that if the path is equal to a full wavelength, you get destructive interference. If it's equal to half a wavelength, then you get constructive interference in this particular scenario. And then you have to go with whatever's given in the problem. Whatever angles are given in the problem, you just have to do some geometry with it and figure it out yourself. There's a million different permutations of this problem, but the main idea is that two main ideas. One, waves do a 180-degree phase change at larger n values. If you reflect off a larger n value, you flip upside down. Two, the idea that waves interfere. Waves interfere with each other. If they're out of phase, they will interfere destructively. If they're in phase, then they interfere constructively. Now we're going to go over a couple of problems, one vertical and one coming in at an angle, and hopefully this will make a little bit more sense.